Hello, today we're continuing in our series on nuclear physics and we're asking this very specific question. Why don't all elements which are above iron 56 spontaneously decay into iron 56? In other words, why doesn't the gold ring or the gold necklace that you might be wearing just suddenly change into iron? Now you might wonder why it should. So let me first put the case as to why you might expect that it should, and then we'll establish why it doesn't. We've already established in the video concerning the binding energy that nature likes a position where the mass energy to start with can be reduced. And the way we showed that is we said that if you took Z protons and N neutrons, individual neutrons and individual protons, and put them, as it were, in a set of scales, this is a thought experiment, and then you take a nucleus which consists of Z protons and N neutrons, but now bound in a nucleus, what you find is that the mass energy, or the mass of Z protons and N neutrons, is greater than the mass energy of the nucleus containing those protons and neutrons. And the differences in mass is converted into energy, and that's called the binding energy. It's the energy which is used to hold that nucleus together, by which we deduced that nature likes to get to a low mass energy. And we've also established that nature has a way of doing this. If we plot the famous NZ diagram, which we've done many times now, where we plot the neutron number along this axis, the proton number along this axis. This line is the n equals z line, which is a purely theoretical line. And what we said is that the stable nuclei initially have n equal to z, but then they divert off like this, such that when you get heavier nuclei, the number of neutrons exceeds the number of protons, and we explained why. And then we said that if you have a nucleus which is just above the line, then in this case it's got an excess of neutrons and it decays by beta minus decay, and that means that the number of neutrons decreases by 1 and the number of protons increases by 1. So a neutron is converted to a proton. On the other hand, if the nucleus is below the line of stability, then you get beta plus decay, where a proton is converted into a neutron. So you go down by 1 proton and up by 1 neutron. If you're well above the line of stability, then you decay initially by neutron emission. You just get rid of all the surplus neutrons until you're into a position where you can do beta decay to get onto the line of stability. And if you're well below the line of stability, you initially proceed by way of proton emission, get rid of excess protons, until you're in a position where you can decay by beta decay to the line of stability. And if you're anywhere up here, then you can do alpha decay, where you get rid of 2 protons and 2 neutrons in one fell swoop to try to get onto the line of stability. But my question is, having got onto the line of stability, somewhere here, let's say here, is iron 56. When you're on this line of stability, why don't you decay to iron 56? And you might ask, well, why should we? And here's the reason. This is another graph that we've plotted many times. This is binding energy per nucleon. So it's binding energy over A against the A number. And you remember that the shape of this graph goes something like this. It hits a peak and then it very slowly tails off. And this peak is at iron 56. And this is the binding energy per nucleon. So if we look at, say, an element out here, a heavy nucleus, a large A, the binding energy per nucleon is less than the binding energy for iron. And let's remember what binding energy is. Binding energy is the depth of the potential well, the extent to which the nucleus is bound. So iron 56 is the lowest value. Binding energy, in a sense, is a negative value. It increases downwards. So this is iron 56, and this, that's that one, And this, whatever that happens to be, would be a lower level, but in a sense, because it's a negative level, it's further up. So if you are here, you can increase your binding energy by falling to iron 56, which means you go down in terms of binding energy to a deeper level, and you give off energy Q. So since that is exactly what nature wants to do, it wants to go to a higher binding energy, which means it goes deeper into the potential well. The question is, why doesn't this element, which might be gold, why does that not spontaneously decay to iron, where its mass energy will decrease and its binding energy will increase, in order to get to the lowest level, which is essentially the highest value of binding energy, in order that you get stability? Why do not all elements, because all elements this side of iron 56 have got a lower binding energy per nucleon, and therefore if nature wants to get to a higher level of binding energy, in other words deeper into the binding energy potential well, it ought to decay. The same, of course, applies on this side of the line, but we'll deal with that later. This time we're simply looking at why these nuclei don't decay to iron 56. That's the case suggesting that they should, but they clearly don't. Well, we'll start off by asking making the case as simple as possible. Here is the binding energy per nucleon diagram again, and here is the shape dropping off, and iron 56 once again is up here. We'll start with the nucleus which has A nucleons, and we'll ask why it doesn't drop to 2 nuclei, each having A over 2. Okay, so our scenario is that we start with a big nucleus which has got A nucleons and let's say N protons, N neutrons and Z protons, and we want to know simply why it doesn't just decay into 2 nuclei, each having A over 2 nucleons, and let's say that will be N over 2 neutrons and Z over 2 protons. We know that it ought to want to do this because if it decays to A over 2, then there will be a higher binding energy, and that means that this amount of energy per nucleon, because this is binding energy per nucleon, will be released. So if you think about this, this is typically going to be something of the order of 7 MeV per nucleon. This possibly will be 7.5 MeV per nucleon. So if this is A is 200, and we're wondering why it doesn't split into 2 nuclei, each of 100, where you would get 0.5 MeV emitted per nucleon, and if you've got 200 of them, that would be 100 MeV that you could get out. Nature surely wants to do this. Why doesn't it? Incidentally, I should make the point that if you split the nuclei into two halves, then those nuclei will be neutron rich and they will have to get rid of neutrons, but that's a second order process. Just to explain why they need to get rid of neutrons, here is the line of stability. Here is the element with a very high A number. It has a certain N, it has a certain Z. If you split those into exactly half, so you've now got N over 2 and Z over 2, that will be here. That's above the line of stability. So the 2 nuclei that you create will have too many neutrons to be stable, so they'll have to get rid of excess neutrons in order to get onto the line of stability. But that will happen after you've split it. Initially, we're just going to think about why it doesn't split in the first place, and then if it wants to subsequently decay, it can do so. So we're going to think about the liquid drop model, and we're going to ask ourselves the question, why doesn't this large nucleus, which is largely spherical, form into 2 smaller nuclei? Now, one of the things we do need to remember is that nuclear material is incompressible. It is as dense as it's going to get. So the volume of the large sphere will equal the volume of the two small spheres. Okay, you can't compress it. So whatever that volume is, this is the volume. It's a bit like a liquid drop. If you take a liquid drop of water, you split it into two drops, the volume of the two drops is equal to the volume of the large drop. Okay, and we know that the mass energy of this here, these two, the mass energy of this is less than the mass energy of this. Consequently, nature wants to get to this position. The mass energy is less because the binding energy is higher. Remember, the binding energy represents the difference between the mass energy of the individual constituents of protons and neutrons and the mass energy of the bound nucleus. So if the binding energy increases, the mass energy decreases. So this mass energy is lower than this. And nature, we think, ought to want to get there. But we need to think in liquid drop terms. How do you get there? Well, you get there by initially deforming your liquid drop to this kind of shape. This is moments before it breaks up and gets to a completely separate, two separate drops. And what I want to ask myself is, what is the position when we are almost at the stage of having deformed this nucleus into this kind of shape just before it breaks up to become two separate nuclei? And we go back to the video that I did on binding energy, and if you remember, we said that binding energy is made up of 5 terms. There's a volume term. This is all described, I'm not going to go over it again, but this is all described in the video I did on the binding energy of a nucleus, the semi-empirical mass formula. We said that the 5 terms were a constant, the volume term times A, and then minus a surface term, recognising that nuclei near the surface are not so tightly bound. And then there's a Coulomb term, recognising that the protons in the nuclei are repelling one another. They are effectively acting against the binding energy, so we have to subtract a Coulomb term from the binding energy term. And then there was an asymmetric term, so we called that A sim, n minus z squared over A. And that reflects the fact, I hope you can see that, n minus z, can I tip that so you can see, oh gosh, I hope you can, n minus z squared. And then there is a pairing term, which is the 5th term, which I'm going to ignore. Let's just assume that these nuclei are all even, so the pairing term just cancels out. The question, therefore, is what happens to this binding energy as the nucleus deforms to get here? We know that once the nuclei are separate, the binding energy is greater, binding energy per nucleon is greater in these two than it is here. That was the chart that if you show binding energy per nucleon against the A number, you know that at iron 56 you get the maximum binding energy. So what we're essentially doing, just to remind you, is we're taking this chart, the binding energy per nucleon against nucleon number, binding energy per nucleon against A number, and we're taking a nuclei with an A number A, and we're asking why it doesn't split into 2, having A over 2. And this has a higher binding energy per nucleon than this. There are the same number of nucleons, of course, because all the nucleons in here go into these two. So the binding energy will increase, the mass energy will decrease. So we're asking the question, why doesn't it do it? And we're looking at this binding energy formula here and asking, how do these terms change as you deform the nucleus? So let's start off with the volume term for this and this. Well, for this, the volume term is simply AV times A. What will it be for this? This is just before the two nuclei break off. So effectively you've got two conjoined spheres of lighter nuclei. Well, the volume term for this is going to be, there's going to be 2 of them, so there's going to be 2 lots of, AV, which is a constant, times A over 2. And the 2's cancel. And so in the left-hand corner, as it were, for the large nucleus, you've got AV times A. And for the two small nuclei, you've got AV times A. And that's hardly surprising because the volume doesn't change. So the volume term doesn't change as you deform the nucleus. No change to the volume term. Let's get this asymmetric term out of the way. So in the left-hand corner, for the large nucleus, you're going to have A sim into n minus z all squared divided by A. And in the right-hand corner, the two smaller nuclei conjoined, you're going to have two lots of A sim into n over 2 minus z over 2 all squared divided by A over 2. Well, let's close the bracket. So this 2 can come up here and multiply by 2 to give you 4. These 2's can come outside, but they're squared, so 2 squared is 4, so you get 4 in the denominator, takes that out. 4 divided by 4 is 1, and what am I left with? A sim times into n minus z all squared over A, which is the same as this. So the symmetric term doesn't change. The symmetric term, remember, reflects the fact that there are more neutrons than protons in the nucleus. That doesn't change as you deform the nucleus. Now let's have a look at the surface. What happens to the surface as you deform the nucleus? Well, let's give these radii. The radius of this is capital R. The radius of this is little r. That's the radius of one of the emerging nuclei. So what are the volumes of those two elements, or those two volumes? The large nucleus will have a volume of 4/3 pi r cubed. The small nuclei, there are two of them, so it's going to be 2 times the volume of each one, which is 4/3 pi little r cubed. But I said that nuclear volumes are incompressible, so those have to be equal. In other words, the volume of these two must equal the volume of this. Okay, so if they're equal, I can cancel out the 4/3 pi on either side, and I'm left with that r cubed is equal to 2 little r cubed. If I take the cube root of either side, I get that capital R is equal to the cube root of 2, which is 1.26, times the cube root of r cubed, which is r. So the large radius is 1.26 times the small radius. The large radius, 1.26 times the small radius. So what does that mean for surface area? Because that's what we're interested in for the surface term. Well, the surface area of the large nuclei, or nucleus, is going to be 4 pi capital R squared. The surface area of the two smaller nuclei are going to be, well, there's 2 of them, so it's 2 times the surface area of one of them, which is 4 pi little r squared. But r is 1.26 little r, so we've now got that 4 pi times 1.26 squared times r squared, which is this here, compares with 2 times 4, which is 8 pi r squared. What is 1.26 squared? Call it 1.5 for cash. So 1.5 times 4 is 6. So on this side we've got 6 pi r squared. On this side we've got 8 pi r squared. This is the surface area of the large sphere. This is the surface area of the two small spheres, right? Surface area of large sphere, surface area of two small spheres. The surface area as you deform the nucleus increases, right? This surface area increases, which means that this surface term increases. And if this term increases, because it's a minus, the binding energy decreases. So as the surface area increases, the binding energy decreases. And finally, we need to think about the Coulomb term, which is ACZ into Z minus 1 over A to the 1/3. That is the Coulomb term for the large sphere. What is it for the smaller spheres? Well, there's going to be two of them. So it's 2 into AC, which is a constant, so that doesn't change, into Z over 2 minus 1, divided by A over 2 to the 1/3. So those are the two we're comparing. This we can rewrite as 2 into AC Z over 2, and then I'm going to rewrite this a little bit here as Z minus 2 all over 2, divided by A to the 1/3, and that 2 to the 1/3 I'm going to bring up here. Well, 2 to the 1/3 is the cube root of 2, we already know what that is 1.26 times 2. Now I can bring this 2 and this 2 here, 2 times 2 is 4, I can bring that outside, so that's now divided by 4. And what I've got is AC Z into Z minus 1 over A to the 3rd, and in this square brackets I've got AC times Z into Z minus 2 over A to the 1/3. Almost the same, almost the same. It's just a Z minus 1 here and a Z minus 2 here. And when you think about it, Z is going to be of the order of 50. So you've got 50 times 49 plays 50 times 48. Not a great deal in it. What's going to matter is this fraction here. This fraction is 1.6 times 2 over 4, which is 0.63. So this is about 2/3 of this. Consequently, the Coulomb effect reduces. And if I show you, let's just bring back the formula. There is the Coulomb term. That is going to decrease, and that's the reason for that is pretty obvious. As you deform the nucleus, the protons within that nucleus are now being pulled further apart. So the Coulomb term, which is a 1 over R term, is going to reduce. So consequently, the Coulomb effect comes down. So what we've shown of the 4 factors in the binding energy formula, 2 of them don't change. The surface term increases, meaning the binding energy decreases. The Coulomb term decreases, meaning the binding energy increases. So the question is, which one of these two wins? Which is dominant? Now, although it doesn't prove anything, it's worth just noticing that the Coulomb value, depending on how you measure it, is approximately 0.7 MeV, whereas the surface term is approximately 18 MeV. And although that doesn't prove anything, in fact, it gives you an indicator of what is true, and that is that the surface term is dominant when it comes to the Coulomb term. So although one is going up and one is coming down, it's the surface term that wins. So the surface term increase is greater than the Coulomb term decrease, and that means that the net binding energy decreases because the surface term has increased, and there's a minus sign here. So let me just remind you again what the implication of a binding energy decrease is. Here's our scales, here's our nucleus, and here are our Z protons and our N neutrons, individual neutrons. And these are the Z protons and the Z neutrons in a nucleus, or if you like, in 2 nuclei, if you split them in half. And what this is telling you is that the difference is the binding energy. So if the binding energy reduces, that means that the mass energy must increase, because mass energy of this is this minus the binding energy. So if the binding energy decreases, the mass energy of this nucleus increases. So what we've just shown is that the mass energy of this is certainly greater than the mass energy of this. That's why we think nature will want to decay. But in order to do so, it has to go through a deformed state in the liquid drop model, and the mass energy of this is greater than the mass energy of this. So if we draw that as a diagram, here's the mass energy, and this is in a sense a measure of deformation. So we've got large nucleus, 2 small nuclei. Mass energy of the large nucleus is much larger than the mass energy of the 2 smaller nuclei. We think that nature is going to take this downward course because that's what nature likes to do. But it has to go via this deformed nucleus, and that deformed nucleus has a higher mass energy. So actually what the mass energy curve looks like is this. It initially has a barrier, and the height of that barrier is called the activation energy. And this is what nature doesn't like. Nature wants to go to a lower mass energy and give off energy as it does so. So it's got a deeper and higher binding energy. But in order to do so, it has to go over the barrier. And there's no energy available. This could be typically of the order of 6 MeV. That's a large barrier. So nature doesn't have 6 MeV ordinarily. And so it can't get over the barrier. And that's why the large nuclei do not spontaneously fall into smaller nuclei and ultimately to iron 56, because they can't get over the barrier. And that's why the gold ring on your finger, or the silver ring, or the silver piece of jewellery that you're wearing, gold piece of jewellery, that's why it doesn't, before your very eyes, break up into iron nuclei. Just as well, really, isn't it? But of course, some nuclei do break up, and we'll find out why that is in the next video.